All right, I'm gonna go ahead and get started, guys. I hit the record already, so I'll just begin with a word of prayer, if you guys don't mind. So, here we go. Dear Heavenly Father, we thank you for this day. I thank you for the students, and thank you for someone coming to get me and remind me we had class today. It was helpful. In your name I pray, Lord Jesus. Amen. All right. Oh, this board is a mess. Oh well. All right. So, questions. You guys have questions? Can you have extra? Let me get my computer out since you guys might have questions about the homework. So what's on the test? Chain rule, right? Yeah.
I've got a question for you. I understand that you've already worked your problem out, but I just have a question on this step right here, going from there to there.
Yeah, let me just steal that from you for a second. So his question's about number 5. I guess is this last year's test? Right? So let's see here. The test is on what? It's on chain rule, it's on implicit differentiation, it's on related rates, it's on the first derivative test, and where is increasing, where is decreasing, concave up, concave down. So in short, pretty much everything you had homework on, right? Who gave this to me? Oh, okay. And this. Yeah. I'll do it. Just a second. I'll even write it down. So, test 2. So I can tell you what I'm going to say before I get into the details. Basically, it's everything we've covered since test 1. That's it. And of course, the material in test 1 is still here. Although it's very unlikely I ask a question about a limit for just the sake of doing it, right? Limits come up from horizontal asymptotes and vertical asymptotes, but that's about it. Okay, so test 2, chain rule. Got to understand the chain rule. And then we did implicit differentiation, which I'm about to do here. Right, so attached with that is finding the equation of a tangent line to an equation, right? So that's one, just the calculation. And so then there's also the application to finding the tangent line, right? To an equation. The curve is defined by an equation. And then the other major application of implicit differentiation we had was related rates. Right? All of those things really have to do with, of course, implicit differentiation. Let's see, what else do we do? We did then first derivative and second derivative applications, right? Applications of first and second derivative, which basically boils down to graphing with calculus, right? And so if you go back to the last class, we did some really big picture examples there where we had to do what? Find critical points, right? Find the intervals of increase and decrease, right? And what was the other thing we did? Yeah, find the intervals of concave up and concave down. What else was there? There were, classify critical points, right? As what? What are your 3 choices? Oh, thanks. What are the 3 choices for classification of a critical point? We got a min, a max, and neither, right? Min, max, neither. Oh, you're right. That's another category altogether. Constant is what the book would say. When we have a bunch of critical points strung together, right, the function can be locally constant. That's also possible. And then, yeah.
Are the critical points chain and concavity?
No, the places where the critical points are just either critical point is defined. What's the definition of critical point? Either f prime of c is equal to 0 or f prime of c does not exist. Those are the critical points. Either derivative doesn't exist or it's 0. So it's either a horizontal tangent or a place where we fail to even have a tangent line. It could also be a vertical tangent. For example, if I have f of x equal to the cube root of x, then what's f prime of x? One-third x to the minus 2/3, right? And so if we rewrite that, that's really 1/3, 1 over 3 x to the 2/3, right? And of course, this goes to infinity. That goes to infinity as x approaches 0. And the reason for that is the cube function, rather the cube root function, looks like a cubic that's been put on its side. And so if I did it right, there's a place here where you've got one of these deals. What's called a vertical tangent. That's also possible. So you can either have the other place where, so here the f prime of 0 does not exist, right? So that's one thing that can happen. Another thing that can happen is something like this. So that'd be something like f of x is equal to the absolute value of x minus 2. If this is 2, you have f prime of 2 does not exist. So that's another way you can have a critical number. But usually, we're just looking for where the derivative is 0. That's almost all of our critical points are that way. What's an inflection point? Right, inflection point is where concavity changes. If it does, right? And the graph doesn't have to have an inflection point, right? Just like some graphs don't have intervals of decrease, right? It could be increasing everywhere. It could be decreasing everywhere. Yep. Oh, okay, good. Is there anything else on my list I need? We did? I mean, we got horizontal asymptotes and vertical asymptotes also, right? And we also have the more basic thing of like zeros of functions. So, yeah.
So for horizontal and vertical asymptotes,
Mm-hmm.
when you're finding the vertical asymptote, isn't that with the denominator equal to 0?
Right.
And then the horizontal asymptote is 1 thing?
The horizontal asymptote, we can see what the horizontal asymptotes are for the graph by looking at x going to infinity or minus infinity.
Okay.
Yeah. So, all right. So I'll finally get back to your question. The gentleman asked me a question about this one. Now, I'm not sure what his question was, but I'll find it soon. So we want to find dy dx is the question, and then find the equation of the tangent line at 2, 1, right? So this is number 5 from the test from last year. Is that right?
Correct.
Okay. So the first things first, we differentiate both sides of the equation with respect to x. So this is the cube function. So I do 3 times x plus y squared. Is the audio working? I forgot to check. Sorry, thanks. Is it good? Okay,
Yeah,
okay.
it sounds identical.
Yay. All right, so thanks. This is 3 times the function squared. Then I have to multiply what? By the derivative of the inside function. Here, the inside function is x plus y, right? So that gives me 1 plus dy dx. And then let's see, on the other side, we just get dy dx, right? Are you okay up to there? Okay.
Why would it be y when you want to
Because ddx,
Oh, because you're multiplying now, yeah.
so ddx of y is just dy dx is the thing. I mean, if I had ddx of, say, y squared, right, then I would have 2y dy dx. Or, let's see here, but the difference is it's y squared. It's not just y. So that was it? That was the thing that was, no?
The next thing about it is the next step that you add
Okay, so what I'm going to do, that times 1. So what I did there was just use a property of algebra, basically. If I have A times B plus C, right? I have AB plus AC. That's okay?
That's fine.
Okay.
We're went from that to now 3 times x plus y squared minus 1.
Well, let's say this is equal to 1 minus 3 times x plus y squared. I might do the algebra different on the solution, but this will be equivalent. The point is I want to isolate all the terms with dy dx to one side. So I've got 1 dy dx over here, right? So there's a 1 here. That 1 translates algebraically to that 1. And then this 3 here, this term, becomes that term. Notice the minus because I subtract it to the other side and factor out the dy dx.
All right. Now I get it.
And now I just divide. Oh, question? Questions are allowed. Dy dx is 3 times x plus y squared divided by 1 minus 3 times x plus y quantity squared. And there you go. Now we found dy dx. If the question was just to find dy dx, we'd be done, right? And now how do I find the equation of the tangent line? Right, so let's see here, dy dx at the point 1, 2, 1. That means x is equal to 2, y is equal to 1. So that's what? 3 times 3 squared over 1 minus 3 times 3 squared. Because 1 plus 2 is 3, so I get 27. Minus 26. What's that? X is 2 and y is 1.
That'd be 1. Not 3 times 3 squared would be 3 times 1 squared. No.
Glad to help. Yes?
Going back up to when you were going from the second class step to where you found dy dx. You have dy dx on the right side, and then it is on the left side of the finished problem.
Right.
Where dy dx equals 3x plus y squared over that. How do you go from that step to find
From here to here? So what I do is I subtract
from
this term right here to the other side.
that to the last?
From here to here? Oh, I just divided both sides by that term. So divide this gives me 1. So basically just
okay.
I switch, this becomes that. And yeah. So does everyone agree with my 27 over minus 26? That's the slope of the tangent line, and so I have the point, 2, 1. The equation of the tangent line then is y is equal to 1 minus 27 over 26 times x minus 2, and there you go. Is that what I got last year? Phew, okay. Good. It's always a moment of concern. Should we do another? Let's do a related rates problem, right? So, suppose you drop rocks onto a conical pile at 1 foot cubed per minute. If the base of the pile is, let's say r is equal to 3 feet, then how fast is the height h of the pile increasing. Can we see that on the, okay. Now, this problem, as stated, would be rather nasty because, I don't know, most of you probably don't know what the volume of a cone is, right? Oh, good. Yay. All right, so prove me wrong. I'm very happy about that. Let's see here. So, although I guess you don't count as most people, but you are a person, so statistically, it's a problem for me. You're a person? You don't deny your personhood? That's good, okay. Let's see here. So this is h, right? And this distance here, the radius, the base of the cone, is what I called r. And you told me the volume, and you're right, it's 1/3 pi r squared h. This is given. I don't expect you to know this from memory or anything like that, all right? Yep.
Which value should we know? What is that?
You should know that area is length times width.
Okay, but like,
You should know that a circle has area pi r squared. Perimeter.
would you give us like a cylinder volume? If that was like an example?
Yeah, I think you should know the volume of a cylinder.
Is it like 4/3 pi or something?
Oh, volume of a sphere I would give
Oh,
you.
volume, yeah.
That's 4/3 pi r cubed, but that I would give you. But the ones that are simple that you can just take the cross-sectional area and multiply by the height of the thing. Yeah, like or if I could even have something more interesting, like, I don't know. Roughly speaking, sorry, I should add holes. I'm always told that I don't have enough holes in my SpongeBob. But now it looks like eyes. I don't know. Anyway, it could be SpongeBob's all the way down. If I give you the area of one SpongeBob and tell you the height, then you can find the volume because it's the area of the typical SpongeBob times the height of the stack of SpongeBobs. Assuming SpongeBob was a two-dimensional entity. I don't know. There are more ridiculous examples I could come up with like this, but my point is if it's something sneaky like that, I'd give you the volume. Yeah. Okay, so then, anyway, not distracting with my stupid SpongeBob. It's too late. I did it. All right, so what then? We relate the rates, right? Just relate the rates. So what's this give us? This gives us dv dt. So what's given is in black. I'm writing the solution in purple. Okay? So dv dt is equal to what? It's equal to 2 pi over 3 r dr dt, oops, times h, right? Plus what? 1/3 pi r squared dh dt. I did chain rule because I mean every time we do the implicit differentiation, there's like a chain rule. The chain rule here was with the squared function. That's why I have the 2r dr dt. What else did I use though? I used the product rule, right? So you guys got to know product rule and quotient rule for this test still, right? Those are important. What?
Did you just split it up as 1/3 pi r squared and then h? So you did the derivative of r squared.
Let's see
and
here.
then-
So this is the derivative of the r squared, and then here's the derivative of the h.
Okay.
And I just,
Okay.
the 1/3 pi is sitting out front. Oh, now we can put in what we're given, right? dv dt is what? That's 1 cubic foot per minute. So pi over 3. 2 times what? R was what? 3. The r dt is what? Oh no! I didn't tell you. Oh man! Given that dr dt is equal to 1 foot per minute. So I'm also going to give you that the base of the pile is also increasing at one foot per minute. If I didn't give it to you, then we wouldn't be able to solve the problem. Okay, so I just said that. Let me make it 2, so we can so you can see where it's going better. So 2 feet per minute. That's why I put a 2 right here. Just to emphasize, this 2 is this 2. That's where that's coming from. And then what was h? We got to figure out h. What is h then? H is pi over 3 r squared in v. So, oh, I got to give you h too, don't I?
Well, could you solve it? Do you know like your starting base? You know, pi.
I need to give. I haven't given you the total volume though. It's still not enough. And h equals to what would you guys like h to be? 4, 7. I think 7 wins. 7 feet.
You're
Yes.
going to give us all this information now on, we're only going to have to solve for one variable on the test. How we're doing.
Yeah, you don't have to add information to make the problem make sense. That's my job. Yes.
Wouldn't the height just be like 1 foot at time 0 if you didn't give us a height? So
Why would it be that?
Huh?
Why would it be that?
Increasing at 1 foot per minute. Like
But that's one
1
cube.
minute,
Well, but that's 1 cubic foot, right? So the question is, 1 cubic foot after 1 minute, does it look like this, or does it look like this? See, those could both have volumes of a cubic foot and be really different cones. That's the rub. So it's ambiguous unless I let me partition off the givens. Okay, there. Now the problem statement is clear. Kind of. So we decided h was what, 7? And then plus pi over 3. What was r? Oh, 3, yeah. Squared, right? And then dh. Now, dh dt, that's what I'm trying to find, right? Our whole goal is to find how fast h is increasing. But there you go. We have numbers and something we don't know, so we can solve for the something we don't know. Right? One equation, one unknown. So dh dt then will be 1 minus, looks to me, 3's cancel. I get 4 times 7, 28 pi, divided by 3 pi, I suppose. And of course that's going to be in feet per minute, given my units. If you'd like, I can find a decimal, but it's probably better for us to go on. Are there questions about this? I mean, yeah.
How did you get that step right before the last one, like all those numbers?
So the
One equals all that.
okay, so the volume. What's the volume rate of change? Well, I say that we're dropping rocks at a rate of 1 cubic foot per minute, right? So cubic foot per minute. That's got to be the volume rate of change of volume, just from the units alone, if nothing else, right? And I told us that the time we're interested in, the radius is 3, right? So that means I put a 3 wherever there was an r, here and here. That's why it's 3 squared. And then how fast is the height h of the pile increasing? Well, that alone wouldn't have made sense. I also need to give you that the base of the pile, the rate of the radius of the base of the pile was increasing at 2 feet per minute. That's why this dr dt became 2. And h being 7 feet, well, that's why I put h is 7 here. Right? And so that was, if I don't give you enough information so that you're just left with the rate of change you're interested in, times the number, then the problem isn't stated. Or there are simpler problems where you know something else that you could figure out the remaining piece of information, like the ladder sliding problem, right? Remember we worked that out? That's a little bit different in the sense that I don't, like, let's see, let's just look at that again for a second here. Remember the ladder sliding problem? If this is a 10-foot ladder, right? If I give you that this point is 6 feet over, then the question is, what's this? See, that you could figure out because you know that 36 plus y squared is equal to 100, which would tell you that y squared is equal to 64, which would tell you that y is equal to 8. You know? And so that problem, if I gave you, you know, if I just give you where one point in the ladder is going and I give you the length of the ladder, you can figure out the other one. The cone problem isn't quite like that because there's lots of different shapes that anyway, let me not try to explain why they're different. They're just different. This one is, but we worked this example out in class, right? So, yeah, I suppose I need to come up with something. So let's suppose that we're given that the top of the ladder is falling down at 2 feet per second when x is equal to 6 feet and y is equal to whatever. The question is then how fast, so how fast is the base of the ladder sliding away from the wall, right? I think I have enough information here. There would be more words, like you're given a ladder, it's 10 feet long, it's resting against a wall, it slides down without losing contact with the wall, and the wall makes a right angle. I mean, basically assume it's as simple as possible. I don't always put all of these words because if I put too many words, it confuses too many people. So I try to strike a balance between saying too much and saying not enough. If you feel like I haven't said not enough, you should just come and ask me, do you mean that this wall's a right angle or something like that? Maybe I wouldn't write that on the test. Maybe I'd just draw a picture to make you think that. So, okay, so the point here is that x squared plus y squared is equal to what? Yeah, 10 squared. Yeah, exactly, 10 squared, which is 100. And so I can relate the rates of dx dt and dy dt. What do I have? I've got 2x dx dt plus 2y dy dt is equal to 0. Oh, by the way, the problem statement was like this shoe. Or giant foot if you like, I don't know, whatever. The purple is part of the solution. So, how fast is the base of the wall sliding away from the wall? You know, and this is to be understood when what? When x is equal to 6 feet. Okay. Not this time, because this. Right, and now, so is dy dt, now we got to be careful. What is dy dt equal to then? So we figured out, let's see, we figured out what? If x is equal to 6, that implies y is equal to what? 8. So we've got that, right? So we've got 12 times dx dt, which is what I want to figure out, plus 16 times dy dt is equal to 0. What is dy dt? No, it is not. See, because y is decreasing, right? -2, right? Yep. I know, right? I know. That didn't come up in the last time I worked the problem because last time I gave you dx dt, which was positive and sliding down, and we derived that the y dy dt was negative. This time I gave you a picture which implicitly says dy dt is negative, but okay, so then what? dx dt is 32 divided by 12 feet per second, I suppose. Yeah. And you could simplify that, but I don't feel like it. So 16, what is that? 16 over 6, 8 over 8/3, right? So it's about 2.67 feet per second, give or take. Anyway, make sure you can do the problems in your homework, right? I oftentimes would ask those in terms of the related rate problems, right? I probably am not going to be super creative and come up with like totally radically new problems. It'd probably just be some simple variation of what you've already seen. Yeah. Ooh, long division to polynomials. I like that. I almost forgot about that. That was from before the break. Let's see here. How about f of x is equal to x squared plus 3x plus 2 divided by x squared plus 6x plus 9. I could say find the horizontal asymptotes and graph it. Now here, long division or something like long division would be a good idea, because that's not a proper rational function, right? A proper rational function is one where you've got the numerator is smaller degree than the denominator. Let's see here. So as per your request, let's see here, that is what? So I need what? One of these? And you subtract, you get what? There's your remainder. So what this says is that this thing up here is actually 1 plus, well, rather minus 3x plus 7. I factored out the minus over here. X squared plus 6x plus 9. Oh, well, once I have that, I can easily see that the horizontal asymptote here is 1. See, because as x goes to infinity, yeah, this goes to 0. So therefore, the horizontal asymptote is y is equal to 1, and that's left or right. Now, you could figure that out without doing this long division, though, right? I don't know if this problem really, really needs long division, but you asked for an example. Yeah, you could just take the limit of this immediately. You know, you could just exactly plug in a big number and see that as well. And also, this one, do you really need long division? Like if you're sneaky, you can just say, well, x squared plus 3x plus 2 is equal to x squared plus 6x plus 9 minus 3x minus 7, right? And of course, this gives me 1. Oh man, did I do it wrong? Well, I added 3x here, right? And I added 9 because that's what I want. But to be fair, if I added 3x, I have to take it away. And if I added 7, I have to take it away. Otherwise, I'm just adding 0 here in a convenient way. But that's the same as long division. This trick doesn't matter to you guys. So let me just make it go away. Don't be confused. There's nothing to see here. Nothing to see here. Nothing to see here. Okay, so how about that? What would the graph of this, well, tell you what, forget about this example. Let's do an easier example. How about this? F of x equals to x squared times x squared minus 9 over x to the 4th minus 16. There. Yes, sir?
I'm stuck on why is y equal to 1? You put 0 into that equation when you get 7 over 9.
If I put, no. If I put a really large value,
Yeah.
yes, if I put 0 in, I totally agree with you. I get 1 minus 7/9.
Yeah.
The value of the function at 0 is indeed 2/9.
Yeah.
Totally agree. But what I'm talking about here is what the function behaves like as we go to infinity.
Really small.
As we go to infinity, that's negligible. And this silly thing is, that's x plus 3 squared, right?
Yeah.
So roughly speaking, this is going to be, let's see here. It's got a 0 at minus 7/3. It's got a vertical asymptote at minus 3. I'd have to think about it more. Yeah, oh yeah. So the graph of this thing, it's got a horizontal asymptote like this, right? And it's 0. Oh, I can't, excuse me, it crosses the y equals 1 line when x is equal to minus 7/3, which is what? Minus 7/3, which side of this line? Yeah, here somewhere. And you just convinced me that 2/9 was the value at 0, right? Which is like here. What?
What did you say when x is equal to 0?
Well, 2/9, yeah. Sorry. Fine. I was trying to abandon this example, but now you guys have got me thinking about it. F prime of x is what? Yeah, we do quotient rule, but it'd be easier. Yeah, use that one. So that's going to be minus 3 over x plus 3 quantity squared. Plus 2 times 3x plus 7 over x plus 3 quantity cubed. I did the product rule there. So the derivative of the, yeah. So the derivative of the, I'm looking at it as the 3x plus 7 function. Well, let's say the minus 3x plus 7 function times the 1 over x plus 3 squared function differentiated. I'm looking at it in that way. And so that's why I get a minus 3 over x plus 3 squared, like that. And then this differentiated gives me a minus 2, but the minus cancels the minus, giving me 2 times 3x plus 7 divided by x plus 3 cubed. Fine. What you guys do to me? I see you're minus 3. Who made this example up? This is all Megan's fault. This is all Megan's fault.
No.
It is.
I made a question.
You asked about the most complicated thing we've done. Let's see here. Plus 3. That's fair enough. You're fine. I'm just. All right. Let's see here. Is that right? I made a common denominator. The reason. The reason. I mean, this particular one will not be on the test. If I was to make a problem like this, I would make it have prettier numbers. Come on. Let's see here. So this is 3x. So 6 minus 3, and then minus 9. What's minus 9 plus 14? Minus 9 plus 14? 5. See, so now I can see where the derivative is positive or negative, right? So minus 5/3 is where you have a critical point. There's also a critical point where? Minus 3, very good. And where would that be relative to this? Yeah. And so we just got to plug in some points to gain a sense of where it's increasing and where it's decreasing. Then I'll be able to make the graph. So how about to the left of, how about like minus 4? If I put in minus 4 here, negative downstairs, because the cube of a negative is still negative. Negative upstairs, it's positive. Yeah, very good. Between here and here, it's going to flip signs again. And then over here, what do we got? Positive, yeah. Let's see here. So, well, there are two asymptotes. There's the vertical asymptote at minus 3. In fact, it's what I'll call a volcano. And then it does something like, well, it does one of these deals, I think. But that's not a very good picture of it, but it goes back to like, it approaches 1 asymptotically as it goes to infinity. So the graph is something like that for this one. How does it pass over the vertical asymptote? Oh, we can cross over. We can cross horizontal. That's a very good question, and very good, very, very good question. I'm so glad that came up. Horizontal asymptotes are fundamentally different than vertical asymptotes in that regard. You can cross horizontal asymptotes as many times as you want. The point is, as you go really far out, you're approaching it. In fact, you could even be on it. It would still be an asymptote. Like, it's kind of stupid, but if I have the function f of x equals to 1, this also has a horizontal asymptote of 1. This one I can graph with considerably less effort. There you go. Indeed, you could have something like it could even do all kinds of crazy junk finitely, but eventually it flatlines. Yeah. Although, sadly, to make these kinds of wonderful wiggles, we really would like to have sines and cosines and exponentials, and as you know, those are forbidden. Yeah? Do you have a question? Oh. No more questions? Yes?
Can you go over, do you have your homework with you?
Yeah, I mean in the computer. Just tell me which one, I'll find it.
For all of these stories.
For more music news, go to popcrush.com.
Silence.
Your home for Aggie football is News Talk 1290. Now, for Rush.
Quiet.
Company simply saves the home.
Shut up, Sean. I want to hear it. Oh, I'm sorry. None of you are named Sean, are you? No. It's a relatively rare name around here. What class are we in? 126. Yes. I gotta make sure I give you guys the right test come Thursday, you know? It'd be awful and give you a 121 test. You really sure you want a 121 test? Do you really want to be tested on the nooks and crannies of factoring cubics at the moment? I think you'd rather have a 126 test. All right, fine. I'll have to. What? Come back. Where are we? www.webassign. Now, which problem were we talking about?
I think I was on the second derivative of like
Homework
homework 6.
6.
Like 6, 7, or 8.
Homework 6.
I'm going to pull that out.
Which number was it?
6, 7, or 8. They're like the second derivative part of the first derivative. I don't know.
These ones. Oh, man, come on. All right, so these ones, yeah? Homework 6. Oh, hey, that was missing from my list. Second derivatives. But, I mean, I told you to study concavity, so, I mean, I guess you would have gleaned it from there, suppose. So, let's see, let's do this. H of x is what? X squared plus 5 squared times x minus 5. And we're supposed to calculate what, the first and second derivative? Let's see here. So first derivative, we've got what? 2x times x squared plus 5. So do you guys see what I did? This is just the derivative of that piece, right? And then plus x squared plus 5 squared times 1, right? Now, before we go to the next step, I know often I tell you guys, differentiate, don't simplify, right? Here you really want to simplify because it makes your life easier in the step that's past this one. So h prime of x is equal to x squared plus 5 times what? Times 2x minus 2x squared rather, minus 10x plus 1.
Why did you add 2x first?
Chain rule, because the inside function is x squared plus 5, so I have to multiply by 2x. So sometimes I would write that
Yeah, what happens to x squared minus 5?
x squared plus 5 times 2x. And I think I lost a 2, didn't I? Is that what you're about to ask me about? Oh yeah, I totally agree with you guys. I missed a 2, which means I should have a 4 and a 20. How did I what?
Yeah, so what did you do again?
4x squared minus 20x.
Oh no.
How did you do that?
Oh no, it's worse.
Yep.
I'm sorry. That's x squared plus 5. All right, your request shall be granted. Here we go. H prime of x is equal to d dx of x squared plus 5 squared times x minus 5. And I will put some big parentheses here to emphasize that's the deal. So that x squared plus 5 quantity squared times d dx of x minus 5. Then we've got ourselves what? We've got 2 times x squared plus 5 times 2x times x minus 5 plus x squared plus 5 quantity squared. Okay, now that gives me x squared plus 5, and then let's see here. if I factor out an x squared plus 5, I can pull 1 from here. There's 1 here, and there's also 1 here, right? But notice the 2, so I have to leave, that leaves me an x squared plus 5 on the second term. Now this one, when I multiply it out, I get 4x squared, and the 2 times 2x, 4x times minus 5, minus 20x. And then this gives me plus x squared plus 5. And then I can collect terms, right? Five x squared minus 20x plus 5, right? Why have I done this? So now I can differentiate again, and it's pretty easy to differentiate, right? So h prime prime of x is what? 2x times 5x squared minus 20x plus 5 plus x squared plus 5 times 10x minus 20. And there you go. If I didn't say to simplify the answer, you could just leave it like that, or you can FOIL it out if you want, I suppose. But, whew. Yowzers. You guys have tired me out. I gotta go. Unfortunately, I'm giving a test in the next period, and I have to go do things. Hey. Thank you. Sorry.